Hello everyone, thank you for watching this video. My name is Brent Griffin. This work is done in collaboration with Jason Corso, and today I'm going to be talking about our work on BubbleNets. With the introduction of high-quality datasets like Davis, we have seen the development of many new video object segmentation methods. This work focuses on improving the performance of semi-supervised algorithms without any changes to the underlying method of segmentation. The current paradigm for semi-supervised video object segmentation is to annotate an object in the first frame and then let the algorithm segment the object in the remaining video. However, we found that providing a different annotation frame changes segmentation performance across the entire video, for better or worse depending on the method of annotation frame selection used. These changes in performance occur due to temporal proximity to other frames and changes in view imposed of the annotated object. To make the best use of an annotator's time, we should select the best annotation frame possible. The goal of BubbleNets is to learn to automatically select the best frame for annotation from an untouched video. Using BubbleNets, we predict relative frame performance to iteratively compare and swap adjacent video frames until the deep bubble sort is complete. The frame with the best predicted performance is then used for user annotation, which is shown in our paper to result in better segmentation performance. Let's talk about how we generate the labels we use to train BubbleNets. Using the Davis 2017 training set, we have 60 videos with dense ground truth annotations of various objects. We train OSFO segmentation using the first frame annotation and evaluate OSFO's performance on the remaining frames of video using the Jacquard measure and contour accuracy. We then use the second frame for annotation and similarly evaluate the performance of OSFO's over the remaining frames. By repeating this process across the entire video, we generate a training label Y for each frame that represents the segmentation performance associated with using that frame for annotation. Next, let's discuss how we use these performance labels to train BubbleNets. While we could use the entire video as input to predict the frame with the best performance, this only provides one training example per video. If we process and predict the absolute performance of each frame individually, we can use a loss based on single frame performance that gives us n training examples per n frame video. Better still, in this work we train BubbleNets using two input frames to predict what we call relative frame performance. By predicting the relative difference in performance of two frames, we formulate a loss that gives us nearly n squared training examples per video, providing extensive training data from the labels generated on Davis. Let's talk briefly about the BubbleNets architecture. Using our relative frame performance formulation, our network input has two comparison frames, I and J, which are pre-processed through ResNet 50. To provide some context for the rest of the video, we also use three randomly selected frames as an additional input. The final input for our network is the normalized frame index of each input frame, which is provided at each of the fully connected performance prediction layers. The final output of our network is the predicted relative performance between the two comparison frames, which uses our relative frame performance loss for training. After training BubbleNets to predict relative frame performance, we can use it to select the user annotation frame on an untouched video. To select the annotation frame, we use BubbleNets in our deep bubble sorting framework, which starts by predicting the relative performance of the first two frames. If the first frame is determined by BubbleNets to have better performance, its position within the sort is swapped with the second frame. After this initial comparison and potential swap, the bubble sort advances to the next adjacent pair for a new comparison. Our deep bubble sorting framework iterates this process forward until the frame with the greatest relative and overall performance is determined, which is the frame BubbleNet selects for user annotation. In general, BubbleNet selected annotation frames lead to better segmentation performance, which we observe in the sort results on the right and when comparing the segmentations resulting from BubbleNet selections versus first frame annotation. We evaluate BubbleNets using the Davis 2017 validation set, with more dataset results provided in our paper. The first thing we note is that first frame annotation, which is the current standard for benchmark datasets, only outperforms last frame selections. Even randomly selecting frames is a better strategy. Middle frame selection is the best naive frame selection strategy and is easy to implement. Finally, the greatest segmentation performance results from BubbleNet selected annotation frames, which provide an over 10% increase in mean Jacquard measure and contour accuracy over first frame annotation. We also emphasize that despite training on OSFO's generated performance labels, BubbleNet selected frames also improve performance of other segmentation methods. Furthermore, our performance label generating formulation can also be used to train BubbleNets for other specific segmentation methods. Thank you for watching our video. If you're interested in using BubbleNets in your own video applications, please visit our GitHub page at the address shown here. And if you want to learn more, we recommend checking out our paper. Thanks.